Hi everybody. This lecture is meant to accompany the Chapter 2 reading in the Corman book, which is Introduction to Algorithms. And this is Chapter 2, and in Chapter 2 we're really kind of just getting off the ground with two relatively straightforward sorting algorithms. First we're going to look at insertion sort, and then we're going to look at merge sort. So you can think about insertion sort kind of like the process that one follows when forming a hand of cards. So, you start out with five cards face down on the table. You pick the first one up and put it in your other hand. Then you take the second card, and when you insert it into your hand, you place it so that it's the order of the two cards is either ascending or descending. And then as additional cards are picked up and added to the other hand, one follows a simple process of simply inserting the card most recently picked up in its correct place relative to the other cards that are already in the other hand. So here in this slide you can see the operation of insertion sort on an array, and this array is called A, and we're using an initialization list to set the array up, and you can see initially we have the values 5, 2, 4, 6, 1, 3, and of course 5 is at sub 0, 1 is at sub 1, or 2 is at sub 1, 4 is at sub 2, and so on and so forth. And if we access the length attribute of the array, that will tell us the number of elements in the array. And you can see that this is an array of integers, and by integer we simply mean a numeric value that doesn't have a fractional component, so no digits to the right of the decimal point. And in the illustration here, you can see we're starting at A and we're proceeding through F. And with each step of the insertion sort algorithm, we're essentially looking at the next key, and we're shifting elements, and then we're dropping the key in so that it's in its correct place in relation to the other keys that are at the left end of this array. So you can see initially, the array is in this particular order, 5, 2, 4, 6, 1, 3. After the first pass, we've positioned 2 in its correct place relative to 5. After the second pass, we've positioned 5 in its correct place relative to the other two keys that are already sorted. And then eventually, as we proceed, we end up with an array in which the keys are sorted in ascending order. And this, again, is the insertion sort. And it's not too difficult to think about this depiction of the algorithm in relation to the analogy on the previous slide in which we have a hand of cards. And from a performance standpoint, if we look at a simple implementation of insertion sort, you'll find that we have a loop inside of a loop. And anytime we have a loop inside of a loop, we're estimating an algorithm that's going to operate in an average sense in quadratic time, which is big O n squared. And we haven't really explored the analysis of algorithm time complexity performance yet, but in this class we're going to look at time complexity performance, we're going to look at space complexity performance, and when we're talking about insertion sort, we're basically talking about an algorithm that performs in quadratic time. And of course, there's a best case scenario, and there's also a worst case scenario. I think the worst case scenario is when the keys are sorted in descending order, and the insertion sort is built to sort in ascending order. And that ends up creating the most work for the algorithm. And I still think we would describe the worst case as quadratic. However, it's at the high end of quadratic. And then if the keys are already sorted and we run the insertion sort algorithm, that's going to lead to the best time complexity performance. And then average, somewhere in the middle, is going to be quadratic time. And that, again, can be attributed to the fact that when we implement insertion sort, we have a loop inside of a loop. And here you can see insertion sort coded up in Java, which is the official language of this course. And you can see we're just declaring a class called insertion sort. We have our main method. We're setting up an array of integers, which we're initializing using an initialization list. And you can see clearly that the keys are not sorted at the outset. We're also declaring 3 integers, I, j, and temp. And then we have a for loop, and we're looping from sub 1 through 1 less than the length of the array, which is going to be the subscript of the maximum element in the array A. And then we're calculating j as I less 1. And this enables us to look at all of the elements in the array at the first iteration of the for loop. And then you can see that as I grows, that so does j. And then inside the for loop, we have a while loop, and we're testing to see if j is greater than or equal to 0, and a sub j is greater than a sub I. And it's when this condition becomes false that we're at the next pass of the outer loop, which is the for loop. And this effectively, inside the while loop, we have code that performs shifting and the dropping in of the key at its right place relative to the other keys at the left-hand side of the array that have already been sorted. And you can see we also have a for loop, a second for loop, which we're using to output the array once it's been sorted. And again, if you'll notice that we have a for loop that has a while loop inside of it, that's a pretty good sign that we're talking about quadratic time performance when we have a loop inside of a loop and we're effectively making a complete pass at the array with each iteration of the while loop and each iteration of the for loop. We basically multiply the number of iterations that the for loop performs by the number of iterations that the while loop performs. And there's guaranteed to be some variability here based upon, the sorts of patterns that can exist in an array of keys that has not yet been sorted. We're going to undoubtedly encounter, ranges that are, practically sorted, and at the same time, we might also encounter ranges that are, not sorted at all. And of course, this sort of complexity is what defines the kind of estimates that we can make on the time complexity performance, because it is an estimation. And just keep in mind that the arrangement of the array at the outset does have an influence upon the actual time complexity performance that we achieve. And then another sorting algorithm that deserves consideration is known as the merge sort. And merge sort was developed at the Institute for Advanced Study in the United States, actually in Princeton, New Jersey. I think in the mid to late 1940s. And this algorithm was initially developed by a mathematician named John von Neumann. And von Neumann came up with this technique. And if you'll notice from this diagram here, that we basically have twice as much memory as the number of keys that we're sorting. So that's one of the drawbacks to merge sort, is the fact that if we have n keys, that we also need an additional n memory locations to effectively run the algorithm. And merge sort depends heavily upon a merge process in which we are initially starting out with the keys in no particular order, and then we start sorting in pairs, then we sort in 4s, then we sort in 8s, then we sort in 16s. And as you might have guessed, this fact that we're sorting in increasing powers of 2, that this is going to give us a hint as to the time complexity performance of merge sort, which is in fact big O n log n. And the log n portion of the time complexity performance estimate is attributed to the fact that we start in pairs, then we go to 4s, then we go to 8s. And that's where the logarithmic time complexity performance aspect of merge sort comes from. There's also a linear process, which is depicted here quite well in part A of the description of merge sort. And you can see that we have this left portion and this right portion, and the left portion is sorted and the right portion is sorted. And then we're essentially selecting the min between left and right, which in this case is 1, and we're dropping the 1 in at sub 9. And then, after we drop the 1 in, the next key that we could take from either the left portion of the split or the right portion of the split is 2, and we drop the 2 in. And as we proceed, we're simply examining the left portion and the right portion to determine where we should drop the next key. And eventually, as you'll notice, we start out with this range of values sub 9 through sub 16, which are in no particular order. And then we break that range, and we end up with a left and a right portion. And as we proceed, we're simply selecting the minimum from the keys that have not already been selected in either the left or the right split. And if you look through this diagram here and you kind of contemplate it a little bit, it isn't difficult to see, just looking here in part B of this depiction of merge sort, you can see at E, we've successfully determined the positions of these keys here, 1, 2, 2, 3. And then we're next looking at 5, so we drop the 5 in. Then we're next looking at 6, so we drop the 6 in. Then we're next looking at 7, so we drop the 7 in. And these infinity symbols at the end of the left and the right splits are tokens which represent the end of the range of integer key values that we're sorting. So that's commonly referred to as a sentinel value, and it enables us to assign a character which represents the end of a sequence of integer key values in memory. And then further visualizing merge sort, you can see our initial sequence. The keys are in no particular order down here at the bottom. And then we're merging into pairs. And you can see each of the pairs are sorted. Then we're merging into 4s, and you can see each of the 4s are sorted. Finally, we're merging into 8, and you can see this is the sorted sequence and that the keys have been sorted in ascending order.